So we're going to start this last video with the maple code for the baseball example. I completely forgot. I thought I had it queued up, but I didn't. But here it is. If you want to see what the dE plot looks like for that differential equation, dV dt equals 32 minus 0.16 times V. By the way, the 0.16, that's just a viscosity constant for air and the shape of the baseball. So it's actually a pretty good representation of how a baseball would travel through air. And in this case, you can see I've added a couple of initial conditions of varying quantities. And it turns out that if you say the initial condition of 200 for the velocity of the baseball, that produces pretty much a horizontal line. So you can tell that it's got some kind of equilibrium solution right about at V equals 200. And just a reminder, you can actually create the title of the graph. You can make it say whatever you want. But if we wanted to, we could just as easily ask Maple to desolve this differential equation. And so I'm just going to say this right here. And Maple will spit out an answer that tells us exactly the same story, but in equation form. This is the solution, the general solution for my velocity equation. And notice, in this case, if I let t get really, really big in the long run, this term kind of disappears. Another way you could see that would be if I take the limit as t approaches infinity of the right-hand side of, in this case, number 2. Oops, I actually have to do Control L. There we go, 2. Maple says, oh, whoops, of course, delimiters, again, close my parentheses. Maple says, it's 200. So if I take the limit of this right-hand side, sure enough, I get exactly what I can see in the graph up there. So back over to our notes page. We have one more page of notes to take a look at. And if you remember from section 1.2, we ended with our example where we had a differential equation for the amount of sugar in the tank. Well, we can actually see what that looks like as a slope field. And pretty quickly you can tell just by looking at the slope field that, hey, it looks like no matter where you start with an initial amount, everything heads towards some kind of a solution in this area right here. So even if we couldn't solve this differential equation, we'd be able to look at its dE plot and say, oh, I know how it's behaving in the long run, just by looking at it. And that's a really handy trick to have when you're looking at more and more complicated differential equations. So the way I like to think of it is you can see what's going on in this area right in here, and you can tell from that in the long run, A of t will head toward about, looks like it's about 670, something like that. 670, and sure enough, that's pretty close. I think it's like 666 to be exact. And so this allows us to take a look at the equilibrium solution, and that's exactly what we found here. So what does this tell us about the function A of t that solves the differential equation? Well, we don't necessarily know what the equation looks like for A of t, but we do know that they all, every single one of these functions, head toward the same equilibrium solution. So if you were the person in charge of that particular tank and somebody said, hey, if we leave this tank running for overnight, what do we expect? You can say, well, we expect the amount of salt or sugar or whatever it was, I think it's sugar, in the tank is just going to level off at this amount. So it's not going to hurt anything to let it run. Or if you have a different shape graph, it might tell you a different story. Another way of thinking about this is the limit we know as t approaches infinity of A of t is equal to some equilibrium solution, right? Whatever that happens to be, whatever number. It's up here, you can read it off the graph, right? And so that means based solely on our knowledge of the inflow and the outflow of a mixture system, we can predict long-term behavior without having to solve. We can predict long-term behavior of the tank concentration without having to solve the differential equation. Now, we've already solved it, so we know we can, so that's not too scary. But that's pretty impressive. And this would work even if we couldn't solve the tank. And this is where qualitative analysis comes into play. This is where it's super useful to be able to look at a differential equation, to be able to look at a picture, a graph of a differential equation, and know what's going on. So we know that we can solve this using Maple as well. So let me switch back over to Maple. And you can see that if I wanted to, I could desolve this, get an equation, even with the initial condition, right? So my initial condition, I can get a particular solution, and then I can take the limit of that solution and prove that, yeah, it turns out to be just about 700, what I expected. So in the long run, we can say that our tank is going to reach a particular concentration. Oh yeah, I forgot it was tablespoons of sugar. And of course, we can see this on our DE plot. And so being able to both see it on a graph as well as calculate it analytically allows us a lot of freedom for being able to solve differential equations. And you can take the limit of the desolve if you want and do it all at once. So notice I'm solving the differential equation, so this right here is going to give me my general solution, and then I can take the limit of that as t approaches infinity, and sure enough I get 2000 over 3, which is the same answer. So there's a whole bunch of different ways so far that we've found that we can use Maple, but really Maple allows us to do all kinds of things that otherwise would have taken us a long time to generate by hand. One of these slope fields is really difficult to make by hand, but Maple can make it in a flash. So that gets us to the end of section 1.3. In section 1.4, we're going to learn how to use numerical techniques to approximate solutions.